Okay, so we will discuss an error analysis. Numerical error arise from the use of approximations to represent exact mathematical operations and quantities. So numerical errors arise from the use of approximations to represent exact mathematical operations and quantities. In fact, numerical error is equal to the discrepancy between the truth and the approximation. So here we can define numerical error as discrepancy between the true value and the approximated value, or the discrepancy between the truth and approximation. For numerical methods, the true value will only be known when we deal with functions that can be solved analytically. So in numerical analysis, we consider the analytical solution as the exact solution or true solutions. Such will typically be the case when we investigate the theoretical behavior of a particular technique for simple systems. One of the challenges of numerical methods is to determine error estimates in the absence of knowledge regarding the true value. So still there is a challenge in numerical methods that how we can determine error estimates in the absence of previous knowledge or knowledge about the true values. So this problem is not yet been solved, but maybe we will solve in the future. For example, certain numerical methods use iteration to compute answers. In such cases, a present approximation is made on the basis of a previous approximation. So this process is performed repeatedly or iteratively to successively compute, hopefully, better and better approximations. For such cases, the error is often estimated as the difference between the previous and present approximations. So here, example is given that certain numerical methods use iteration to compute answers like iterative methods. So in such cases, a present approximation is made on the basis of previous approximation. This process is performed repeatedly because an iterative algorithm is the algorithm that can apply to solve the problem repeatedly. So that is why we call these iterations. Okay. So uh, number of attempts by the algorithm to solve the problems. For such cases, the error is often estimated as the difference between the previous and present approximation. The next is the floating point arithmetics. So what's the problem behind floating point arithmetic is that computers can store integer exactly but not real numbers in general. So instead they approximate them as floating point numbers. So the fact is that the computer is unable to store integers. Computers can store integers only and exactly, but is not able to store real numbers as it is. So we actually convert real numbers as floating point numbers to adopt a standard format. So a decimal floating point or machine number is a number of the form. It means machine numbers are also the decimal floating points, and the decimal floating point is also called machine number. The standard form of the machine number or floating point number can be expressed as plus minus 0.d1, d2, so on, dk multiplied by 10 power n. where digits this di lies between 0 and 9. It means that d1 can have value from 0 to 9, d2 can have value from 0 to 9, and so on. Dk can have value from 0 to 9, whereas d1 cannot be 0. So this d1 cannot be 0, where m denotes mantissa. So it means the number of digits from d1 to dk is the mantissa, or significant or fractional part. So this mantissa is called significant or fractional part, and n denotes exponent, which is a fixed length integer. So now to understand how machine number works, consider a simple computer where m is 3 digit long and n is 1 digit long. The smallest positive number this computer can store is 0.1 multiplied by 10 power minus 9, and the largest number is 0.999 into 10 power 9. Thus, length of the exponent determines the range of numbers that can be stored. So if n is 1, so it means we can store a number from 0 to 9. And if m is 3, so we can store a number from 000 to 999, and we can adjust our point before this 3 digits. So that is why the highest number that computers can store under this format, 3-digit format, is 0.999 into 10 power 9, because n is equal to 1. So you cannot write 10 power 10 or 10 power 11, because if you write 10 power 11, so then n will be 2. So now n is 1, so you can store from 0 to 9. So thus length of the exponent determines the range of numbers that can be stored. However, not all values in the range can be distinguished. Numbers can only be recorded to a certain relative accuracy. For example, for simple computer as defined above, next floating point number after 1 is 1.01. So if first number is 1, so then the next number is 1.01. So the quantity, the difference between these two numbers, you can say that if 1 is the exact value and 1.01 is the approximated value, so then the discrepancy between these two numbers is 0.01, which is called a machine number. Is the worst relative uncertainty in the floating point representation of a number. So that is actually the difference between two consecutive numbers. So now what is chopping and rounding? There are two ways of terminating mantissa of k digits decimal machine number, that is chopping and rounding. Recall the floating point number as given below. So plus minus 0.d1, d2, so on dk, dk plus 1, dk plus 2, so on, multiplied by 10 power n. And di is this d1, d2, d3 lies between 0 and 9. And d1 is not equal to 0. So definition, in chopping, floating point number could be approximated to k digits floating point number by chopping off the digits after k. So if the number is 0.d1, d2, so on, dk plus 1, dk, so we can chop off the remaining digits after k digits, so k plus 1, k plus 2, so on. Okay. Such that floating point number will take the form as given below. So after chopping, this number will become plus minus 0.d1, d2. so 1 dk multiplied by 10 power n, and this di lies between 0 and 9. So d1 is not equal to 0. Now for the rounding, in rounding floating point number could be approximated to k digits. K digits floating point number in two steps. In rounding, floating point number could be approximated to k digits floating point number in two steps. First, chop off the digits after k digits. It means you need to chop off digits dk plus 1, dk plus 2, and so on. And then you have to add the quantity 5 into 10 per n minus k plus 1. So if dk plus 1 greater than or equal to 5, then add 1 to dk before chopping. So the example is that consider the floating point number pi is equal to 3.1415926535, so on. If we wish to obtain 5 digits floating point form of the number pi, consider the floating point number. So this is the number pi. If we wish to obtain 5 digits floating point form of the number pi, then using chopping, the number will be pi is equal to 3.1415 multiplied by 10. And using rounding, the number will be 0.31416 into multiplied by 10 power 1. Example 2 is consider the floating point number 2 by 3 is equal to 0.666. If we wish to obtain 5 digits floating point form of the number 2 by 3, if we wish to obtain 5 digits floating point form of the number 2 by 3, then using chopping, the number will be 2 by 3 is equal to 0.666, and using rounding, the number will be 0.6667. So here is an example of uh, rounding. So the actual number is 0.666, but in rounding, we has to add the quantity like 5 into 10 per n minus k plus 1. Then using chopping, the number will be 2 by 3, and using rounding, the number will be 0.667. But if k plus 1 digits is less than 5, then there will not be any increment in the last digits. For example, if we have the number 1 by 3 is equal to 0.333, using chopping and rounding will be the same as 0.333. So then approximating errors, all numerical methods involve approximations due to either limits in the algorithm or physical limits in the computer hardware. So all numerical methods involve approximations. It means, so we have numerical methods, and these numerical methods involve approximations due to either limits in the algorithm, it means software, and limits in computer hardware. Let P denotes exact computation and P star denotes numerical approximated value. Numerical approximated value of a function. So then two measures of the error can be defined as follows. So first is absolute error. That absolute error can be defined as epsilon is equal to true value minus approximation is equal to epsilon is equal to p minus P star. There are numbers of ways to describe errors in measurements and calculations. The simplest is the absolute error. This is the difference between the measured or calculated value and the true value. There are a number of ways. There are a number of ways to describe errors in measurements and calculations. The simplest is the absolute error. This is the difference between the measured or calculated value and the true value. So then relative error, the relative error can also be multiplied by 100% to express it as. So true value minus approximation over true value multiplied by 100 is called relative error. Or instead of using true value, we can say that current value or current approximation minus previous approximation over current approximation multiplied by 100. Or if we denote this true value with P and the approximated value with P star, or if we denote this current approximation as P and previous approximation as P star, so we can write as P minus P star absolute over P absolute multiplied by 100. So P is not equal to 0. The shortcoming of the absolute error is that it does not take into account the order of magnitude of the value under consideration. One way to account for the magnitude is to consider instead the relative error. A shortcoming of the absolute error, so it means there is a drawback for the absolute error. So what is the drawback? That it does not take into account the order of magnitude. So it cannot tell you what is the order of the magnitude or how much percent is the error. But the relative error tells us that it is 100%, 20%, or how much percent. So the next example is, consider the following example which shows different absolute errors but same relative error. So assume that P is the true value and P star is the approximated value, and what is the difference is 10 power minus 1. And next we can take the same value but multiplied by 10 power minus 3, and the difference is less than the previous one, because here is 10 power minus 4 is 10 power minus 1. And here assume that P is equal to 2 into 10 power. So this is not minus 3, this is 3 plus 3. And P star is 2.1 into 10 power plus 3. Okay. So again the difference is 10 power 2 mean it's 100. And so if we calculate, so if we calculate this, the relative error, so relative error is same in all these cases. So here we can add a remark. Accuracy refers to how closely a computed or measured value agree with the true value. So what is the accuracy? It means accuracy is actually that the computed value and measured computed or measured value, how it is close to the true value. Precision refers to how close measured or computed value agree with each other after after repeated sampling. So what is the precision? Precision is actually the difference between the measured values, and the accuracy is the difference between measured value and the true value. And now the sources of errors in numerical approximation. So it is observed while numerical approximations through numerical approaches that there are at least two sources of errors. Round off errors. So errors caused by the imprecision of using finite digit arithmetic in practical calculation, for example, floating point numbers. Round off error is a characteristic of computer hardware. Any arithmetic operation among floating point numbers should be thought of as introducing an additional fractional error. Any arithmetic, so here is the point to be noted, any arithmetic operation among floating point numbers should be thought of as introducing an additional fractional error. Such kind of error is called round-off error. So example is that consider the floating point number x is equal to square root of 2. The 4 digits floating number is so x subscript star is equal to 1.414. We can write this as 0.1414 into 10. Performing 4 digits arithmetic, square of x star is given by x star square is equal to 1.999. So value x star square is equal to 1.999 is not equal to 2 due to round off error. So round off errors originate from the fact that computers can only represent numbers using a fixed and limited number of significant figures. Thus, numbers such as square root of 2 cannot be represented exactly in computer memory. The discrepancy introduced by this limitation, in which is round off error. Even simple addition can result in round off error. So next is the truncation error. Often Taylor series is used to approximate a solution which is then truncated. Consider Taylor series expansion of trigonometric function sine of x, which is sine of x is equal to x minus x cube over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial plus so on. So practically we cannot use all of the infinite number of terms in the series for computing sine x. Usually we terminate the process after a certain number of terms. An approximation error due to such kind of termination or truncation is called as truncation error. So again, the discrepancy between true answer and the answer obtained in practical calculation is actually the truncation error. So how we can calculate this error? For example, derivative of a function at point is given by the definition of derivative d by dx at x naught is equal to limit h approaches to 0 f of x naught plus h minus f of x naught over h. On computer, we cannot take h approaches to 0, that is, there exists a smallest positive floating point number. Therefore, h must take a finite small value. So now using Taylor's theorem, we can expand this term f of x naught plus h. F of x naught plus h is equal to f of x naught plus h f of x naught plus h square over 2 factorial f double prime at xi where xi lies between x naught and x naught plus h. So then we obtain the same term involved in derivatives, but still we cannot write h approaches to 0 because we must have to select a small number instead of 0, and we have to given this value to h. So here we show some limitations that computer can have. Consequently, using a finite value of h leads to a truncation error of size equivalent to h by 2 into absolute value of double derivative of f of x2. So that is the you can say the idea of the error, how errors are introduced or how these errors can be measured. So the floating point arithmetics is basically uh, the idea to calculate these errors are just to reduce the errors to improve the accuracy. So that is why these truncation errors and round off errors choppings are very useful just to get the maximum degree of accuracy and to reduce the discrepancy between two values, that is the true value and the approximated values.